sure I'm recording here. Before we get into that, I wanted to just kind of walk through. And so I'm going to call you name by name. And I want you to tell me, let me get here. I want you to tell me which rule you're going to use from the beginning. Okay. So what that means is you have a few choices. You can use any of the 4 special rules, and hopefully you have your formula sheet in front of you so that you can refer to that. And then there's the product rule, the quotient rule, the chain rule, or a combination of them. Okay, so I'm just gonna go down the line and ask you to identify. And if you need help, call in a friend, ask someone to help you out. But I think you guys will have it at this point, but that's what I like to do is just make sure that we all got it. Okay, so Gennaro, I'm going to start with you. So which rule would you use?
Is it the quotient rule?
Okay, you're absolutely right. Now, can you get out of the quotient rule on this one?
I believe so.
Okay, do you know how you would do that?
Hold on, sorry. I need to pull out my formula sheet. Sorry, I'm trying to
That's
find
okay.
it.
That's okay. Well, this one you don't really need a formula sheet. If you look at it, notice this x squared is divided into both the x to the 5th and the -1. So whenever you see something like this, when it's a single term on the bottom, you can actually rewrite it like that. And then you can simplify because x to the 5th divided by x squared is x cubed. And then this 1 over x squared, I can rewrite it as x to the -2. So you absolutely can get out of the quotient rule. You would get the exact same answer, right? So it's not wrong to use the quotient rule. It's just one extra step that you may or may not need. Okay, and then you can use the power rule from there. Does that make sense?
Yeah, I see it now. Thank you.
Okay. All right, let's see who's my next victim here. Orlin, what would you use?
Product.
Okay, product rule, yes. And then is there a way for you to get out of the product rule? So when you look at it, look at what you're doing with it. And so do you see how it's x cubed times the parentheses?
Mm-hmm.
So you literally could take it and multiply through. So you just distribute it through. So you end up with x to the 5th plus x cubed, and then you can use the power rule. Okay. But again, just like that first one, you can use the product rule. It works. You'll get the exact same answer, but always look for a way to get out of it. And sometimes you can, and sometimes you can't. Okay.
So this way, it's just easier and quicker.
Yes. Yeah. It's that work smarter, not harder. That idea. All right. Let's see. What do we got next? Gabe, what would you use on this one?
Is it the chain rule?
Yes, very good. And there's no way to get out of it, right? The only other way that you could do this is if you multiplied that trinomial by itself and then that answer by itself again. So that's a lot of work. It's a lot of algebra. There's a lot of times, ways that you can make mistakes in that. So the chain rule just works way easier. You just drop that 3 to the front, repeat, subtract 1, and then times the derivative of the inside. Very good. Okay, Nathaniel, I know you just walked in or just came in. What we're doing is we're just identifying which rule would you use. So Nathaniel, which rule would you use on this one to get the derivative? And if you're talking, I can't hear you. So you have to unmute yourself. Nathaniel, are you there? Did you get bumped out? There you are. Okay, I do see you. Can you hear me okay?
Yes, ma'am, I'm here.
Okay, all right. So Nathaniel, what we're doing is we're just identifying which rule you would use to find the derivative. So your choices are, you have those 4 special rules, the product rule, the quotient rule, or the chain rule, or a combination.
This one is one of the 4 special derivatives. I don't. Is it? I know it has the ex in it, so it's derivative of ex.
Mm-hmm.
But I
Yep.
don't know. Is that the name of it? Like the official
Yes,
name?
it's just it's the natural number, but e to the x is e to the x. So yes, you're absolutely right. Very
Okay.
good. Okay. All right. And then the next person is Genevieve. Which one would you use for this one? Let's see, is Genevieve here? Thought I saw her come in. Oh, sorry. I guess she's not here. Okay. Lauren, which one would you use?
I'm a little confused. I don't quite get the rules.
So do you have let me show you. Do you have the, let's see, how do I get out of this? The formula sheets that are available to you?
I was trying to find those just now.
Okay, all right, yeah, so those are if you look in your Canvas where it says in class PDFs or PDFs used in class, it's in module 2. There's a formula sheet and it's got all the formulas in it. So you definitely want to make sure that you know how to use those. So on this one, this is one of your 4 specialty rules, right? So it says the log of any base. So the derivative of that is 1 over x ln of 3. So all we're doing is we're plugging in whatever the base is, goes here. Oh, sorry. Hang on. I was doing it answering the actual question. So you're going to put your base here right there, and then the x goes here. And so it's literally just a tool that we use to get the derivative. So there's no like math to it. It's just, this is the tool that you use and this is how you use it and you place it in the right spot. Okay, so that would be the log rule, one of the log rules.
Okay.
Okay, all right, Evan, you're up next. Which one would you use for this one?
My bad, miss. Can you hear me?
Yes.
Okay. I'm kind of bad at these ones too, but is it it's not the quotient one, is it?
No, because quotient would be division. So what are you
Yeah.
showing there? Like what operation?
Oh, multiplication, but
Yeah.
I forgot which one the multiplication is though.
So think about the answer to a multiplication is the product. So it's the product rule.
Okay.
Okay. So
Okay.
the other way that we can do this though, remember you can do FOIL, right? And
Mhm.
again, the product and quotient rule, they work great. But if you can get out of them, then get out of them. So square root of x times square root of x is just x. Square root of x times -2 is -2 square root of x. 2 times square root of x is +2, square root of x, and then 2 times -2 is -4. So what's nice about this one is, do you see how it all drops to that? Because these cancel each other. So
Yeah.
if you use the product rule, you would have gotten the same answer, right? It would have been 1, the derivative of this. The derivative of this function is 1, and it would have worked out and it would have all broken down to 1. But man, is this so much easier than trying to, do the derivative of the first times the second plus the first times the derivative of the second. So a lot of times what happens is in math is if you can find an easier way, use it. It'll just makes your life much easier. Okay, Javier, what are you going to use on this one?
The chain rule, and we also can use the product rule.
Perfect. So the chain rule and the product rule. So this is the one that probably blew your mind a few times on Tuesday, where there was just a lot going on. But the whole point of this activity right now is, can you identify which one to use? Okay, and then you'll have to go in and just practice. And I can tell you right now, on your test, because I just looked at it, on your test, you have one like this. So you definitely want to know how to do this. Okay, so you want to practice that, the chain rule plus the product rule. Okay. And the easiest way, I'll just start it for you. We won't go through the whole thing. But the easiest way, remember, anytime you have the product rule, you want to do the first and derivative of the first, the second and derivative of the second. So you want to take this big formula, big equation, and you want to break it down into chunks, right? So the first is the 2x minus 1 cubed. And the second is the 2x plus 1 to the 4th. And then you're going to find the derivative of each of these. So the derivative of this is the chain rule. So we bring our 3 to the front, repeat, subtract 1, and then times, don't forget this part, times the derivative of the inside. So the derivative of the first ends up being that 6 times 2x minus 1 squared. And then same thing over here. Drop your 4 to the front, repeat, subtract 1, times the derivative of the inside. So you end up with 8 2x plus 1 cubed. Okay, then you have your 4 cast of characters. As soon as you get your 4 cast of characters, you're just plugging it into that product rule. Okay, now again, on the test, if you do all this, you show this and you plug it into the product rule, you're good. There's nothing else that you have to do to earn the full credit. If you want to earn extra credit, then you'll simplify it by factoring out what's in common. Okay, so my goal is that you can do this and put it in the product rule in the right spot. Okay, any questions on that? Okay. Oh, go ahead.
No, I said no.
Okay. All right. Let's see. Matthew, you're next. Can you say that again? You were kind of cutting in and out. Okay. Okay, so power rule here. And then what about here? I'm having a hard time hearing you. Yeah, you must have a bad connection. So ln, right? Derivative of ln is 1 over x. And then this one is e to the x, so it's just e to the x. So you have 3 different things going on. So that's that idea that it's a combination, right? So you have the power rule, you have ln, and you have e to the x. So again, you take one big giant chunk and you break it up and you just concentrate on each one individually. And if you do that, then when you put it all together, you end up with the correct derivative and you're good to go. Okay, I think that's what you were saying, Matthew, I hope. Oh, very good. I gotcha. Okay. Oh, darn it. I didn't erase it. Why? Huh. I don't know why it's not letting me erase. All right. Next one. Okay. Let's see, George, how about you? What are you gonna do on this one?
The quotient rule?
Okay. And is there any way to get out of it?
The product?
No, there's no way to get out of this one. And if you notice the bottom, the denominator is a binomial. So that's how you know. The only way to get out of the quotient rule is if on the bottom is a single term, what's called a monomial. But because there's two parts to it, you can't get out of it. So you got to do the quotient rule. Good. Okay. And Cassandra, how about this one?
That would be a derivative of EX.
Okay. Okay, now this is one that remember this is that function f of x is e raised to a function, right? So the derivative of that is e raised to the function, so you repeat it, times the derivative of the function. Okay, so this is a little bit different. So what you're doing is you're actually using the chain rule for this. So we're going to find the derivative of this is I'm going to just repeat it. So 3e to the negative 6x times the derivative of the function itself. So times negative 6. So then I can combine these two. So negative 18 e to the negative 6x, and that is my derivative. Okay, so if you have something other than just plain x, then you have to use this chain rule, this specialty e to raised to a function. Okay. All right, Mahmoud, you're next. Which rule would you use? Mahmoud, can you hear me?
Yes, ma'am. Sorry.
That's
My
okay.
mic wasn't working.
Oh, okay, no problem. So what would you use?
Wait, I can't see the full question. Okay. The one with the one without the logs. I forgot what it's called. I'm sorry. Wait.
So when you look at it, what are these two sets of parentheses doing?
Multiplying together?
They're multiplying, yeah. So whenever you're multiplying, you can use what's called the product rule. Oops. The product rule, right? We can do that. Or because there's no exponent, right? The exponent is just 1 on both of these. You can actually just distribute this through, right? Distribute through, and then you end up with x to the 7th plus 8x to the 3rd, and then distribute and distribute. So what we're doing is we're getting out of using the product rule.
Yes,
By
ma'am.
just multiplying, which it just kind of cleans things up for you. And it keeps you from having to do the product rule. But if you choose to do the product rule, you'll get the exact same answer. So it's not wrong. I don't want you to feel like you're doing it wrong if you do the product rule. It's just two different ways to do it. It's how you see it, and then trying to make it as easy on yourself as possible. So with this one, you can see there's no like terms, right? So this product rule is going to be very long and involved when you use the product rule. Otherwise, when you multiply it all out, now I can just use the power rule. But it's still a lot, right? There's still a lot going on. And then the 40 goes to 0. So this would be my derivative. And so either way, whether you do the product rule or whether you do the multiplying it out and then getting the power rule, both work. Okay. All right. Last couple, I think. Is that it? Oh no, I got a couple more. Let's see, Dylan, what would you use for this one?
The quotient rule?
Quotient rule. Good. And any way to get out of it?
Yeah, no.
No, can't get out of it. Just got to set it up. So again, just like the product rule with the quotient rule, you're going to do your forecasted characters. Okay. And then Brian, last one. Which rule would you use, Brian? Or rules?
All right. Would it be the chain rule?
Okay,
the
chain
quotient rule?
rules involved. But then there's one other one. I think you said it.
The quotient rule?
Yeah, so you have to do both. So this one, anytime you have an exponent on the outside of something big, just break that up. That exponent goes to each piece. Just like that. Okay, because it's going to be applied to both of them. So now you're going to use the quotient rule with the chain rule. Okay, and there's no way to get out of it. You just got to go with it. Okay, so the quotient and the chain rule on that one. Okay, so definitely practice for those of you who don't feel confident. Oh, darn. Wow, that happened fast. It just shut down on me. I am so sorry. Okay, I got you now. I got you. Thank you for staying. Well, a lot of people would go, yes, she's gone. I'm done. Okay, sorry about that. Okay, so make sure that you guys are comfortable with the knowing which rule to use when. Okay, that's going to be the biggest challenge, is knowing which rule to use when. And it's just an identifying factor. You have to look at it, identify it, and so on. Okay, so what we're going to do today is we're going to talk about implicit differentiation. So far, what you guys have been doing is what's called explicit. You guys have been doing explicit differentiation. And what it looks like is, so for instance, you know, all the ones that we just had, even if it was, you know, the product or the quotient rule, like that one, all the variables are x's, right? Every single function that we've been working with has been in terms of x. Okay, now what we're going to do is now what is called implicit differentiation. We're still finding the derivative, but now we have functions that look like this. So this is actually what's called a non-function. So remember, let's see, let me get back to it. When oh darn, I lost it. I lost that too. Hang on, let me grab it. So up until now, you guys have been doing functions, right? Just things that look like that. So if you remember the vertical line test, right? If I put a vertical line through any graph and it hits one place, get the right color here, it hits one place, this is considered a function. Okay, now what we're going to do is we're going to start with non-functions. So this is an example of a non-function. Get this out of the way. Okay, so what that means is if I put a vertical line through this function, you can see it hits in two different places, right? So it makes it much more challenging. So if I said, what is the slope, because remember, we're still talking about derivative, what's the slope right at x is 2? Well, we have a slope that looks like that at x is 2, but we also have a slope that looks like that at x is 2. Okay, so we have a problem. We have two different y's. So this is 3.5 here, 3.5 here, and this is negative 3.5 here. So we have two different y values, one x value. So this is, you know, if I put a vertical line through it, I'm going to hit this function in two different places. So it's not a function. So we have to be able to have a way to find derivatives on non-functions. Okay, and that's what implicit differentiation is all about. So how this works is when we're working on implicit differentiation, we're working in two different scenarios. Okay, we're working with a set of instructions that says find the derivative. So this d dx says find the derivative in terms of x. In other words, how is my function changing or non-function? How is my graph changing? What's the slope in terms of x? Well, if I have an x squared plus y squared equals 10, all of a sudden I don't have a function anymore. And so I have a variable that's different than what I'm looking for. Okay, so I know what I'm going to ask you to do is redundant, but it's going to come into play and it's going to make it super easy for you to follow the process if you will just do this redundant step. Okay, so what we're doing is this is the instructions, find the derivative, right? That's our action. This dy dx, that is the derivative. So this right here, this dy dx is what we're looking for because we're looking for the derivative. Okay, so in every implicit differentiation type problem, you want to make sure that you can find the dy dx. There's got to be a dy dx that you're going to create within your function. Okay, so what happens is if I go through and I find my derivative, let's say I find the derivative right here at that point, my slope is going to be a negative slope, right? Because going back to basic algebra, the line is going downhill, so I'm going to have a negative slope. But at this point, same x value, right? Same exact x value, I'm going to have a positive slope. All right, so because I have the same x value but two different y values, our answer has to have a y in it so that we can find out what the slope is at a very specific point. So remember, derivative is the instantaneous rate of change. So we should be able to find the slope at a very specific point, even if we have x's and y's. Okay, so here's how this works. You're going to differentiate. That just means find the derivative on all terms with respect to x. So that's your d dx. Okay, so I'm going to do this in a different color because it's not really part of the answer, but it is part of the process. So I have 3 terms. So I'm going to write d dx for every term. So what I'm doing is I'm taking and I'm exploding out this function or non-function, this equation, so that I can differentiate every single term. So the first one says, find the derivative of x squared in terms of x. So notice I have the exact same variable, right? My variable's good to go. All I have to do is use the power rule. And I'm done with that one. Okay, it says find the derivative of x squared in terms of x. So I have an x, I'm good to go. The second one is where we end up getting into trouble, because it's saying find the derivative of y squared in terms of x. Well, we don't have an x. We only have a y. So that's why this step is so important, because it identifies, oh, my variables are different. Okay, so here's how we're going to do this. We're going to use the chain rule. We're going to peel off the 2. So the derivative of y squared is just 2y. And if I peeled this 2 off, what's left, and I'm going to change my color because this is what I'm looking for, what's left is dy over dx. So what you can look at that as is dy or d dx times y over 1. So you're literally looking at it as if it's you're multiplying fractions. I peeled off the 2 and I got 2y. And what's left is my dy dx. I'm going to put my squared back up here. Okay, so once I peel this 2 off and I get the derivative, and it's just the power rule, right? Derivative of y squared is 2y. When I have different variables, I have to have my dy dx. That's where the dy dx comes in from. And that is my derivative. And then the derivative of 10 in terms of x. Well, some people are going to look at that and say, well, there's no x there. Well, there is an x there. It's x to the 0 power, which is just 1. So when it's just a constant, we're just going to go back to the derivative of a constant is just 0. Okay, so let me walk through it one more time. I'm going to find the derivative in terms of x of every single term. My first term, x squared, my variables are the same, so I'm just using the power rule. My second term, my variables are different, so I'm going to use the chain rule and implicit differentiation. So derivative of y squared is 2y. I peeled that 2 off, and what's left is dy over dx. Okay, and then the derivative of 10 is just 0. All right, once you get this set up, now you're just doing algebra. That should be a dy. Okay, all we're doing is we are solving, we are trying to isolate that dy dx, because that's what we're trying to find. We're trying to find the derivative. Okay, so we're going to solve for dy dx. So how do I do that? I bring my 2x over by subtracting 2x. And I'm going to move up here. So I end up with 2y dy dx equals a negative 2x. And then I'm still trying to get my dy dx by itself. So this is 2y times dy dx. So I'm just going to divide both sides by 2y. And then I'm going to simplify. So my dy dx equals, so negative 2 over positive 2 just cancels to negative x over y. And that is the derivative. Okay, now let's see how this works. So let's go back up here to my circle, right? So let's say this is 0.2 here. We're just going to make up numbers, right? And let's say this is my y value is 3, and my y value here is -3. Okay, so when x is 2, what is my derivative? Well, when x is 2 and my y is +3, I end up with a negative slope. Do you see how it's negative? It goes downhill. If I wanted to find the slope here, when x is 2 again, and my y is -3, I end up with a positive slope. So my derivative will work based on which y and which x I'm plugging in. Okay, so that's why that's the reason you have to have a y variable, because you have a non-function, your x is the same, but I have two different y's that I can look at. And so now I can be very specific. I want to find my, and this is how it's going to look in your My Math Lab. I want to find my derivative at 2, 3, and then my derivative at 2, -3. And I'll show you this in My Math Lab. So this indicates, all right, now we know what x and y are. Now we can plug it into our derivative. Okay. All right, any questions on that one? Okay, so let's just keep trying. Just practice is how it's going to get comfortable for you. All right, now when I taught this in class yesterday, in my face-to-face class, we went through it all, and then I walked around and was watching how students were practicing it, and they totally disregarded me saying, make sure you do ddx in front of every term. Okay, and it came back to bite my students in the very last question because they didn't take me seriously, because the variables are going to change, right? When we get into our word problems, we're going to find things like the derivative in terms of time, or the derivative in terms of pay, or the derivative in terms of hours. Our bottom variable can change depending on what we're looking at. So it's in the ones that we're doing right now, it's always going to be ddx, but it depends on what we're looking at. So that's why I say you have to be really diligent about writing that, and it is redundant. I get it. It is redundant. In other words, we're going to do it over and over and over again. So I have two terms, so I'm going to write it 2 times. And I'm doing it this way just so I don't have to keep changing my pencil or the pencil color. So I have x to the 4th and y squared. Okay. So I'm finding the derivative of x to the 4th in terms of x. So my x's are the same. I'm good to go. I just use the power rule. Here, I'm finding the derivative of y squared in terms of x. Well, these are different. Okay, so I have to find and use my chain rule. So I'm going to peel off that 2 and get 2y. And then that 2 is gone. So what's left is dy dx. So this is that implicit differentiation idea. I'm implicitly finding the derivative. I found the derivative of y squared is 2y. And then I'm finding the derivative of y in terms of x, so dy dx. Okay, and again, every time I have different variables, I'm going to end up with this dy dx. Okay, so here I can divide both sides by 2y. So I get my dy dx equals, and I'm going to simplify, 4 divided by 2 is 2, x cubed over y, and there's my derivative. So just kind of take a look at it. Make sure you understand where all the values came from. That was a 2. Anything throwing you? Okay, so now we're going to get a little more complicated, right? We're going to look at it. We're going to go, okay, when I look at number 3, it's x cubed times y to the 4th equals 20. So the first thing that I see is I have product rule. Because I'm multiplying 2 things. I cannot put that x and y together. I have 2 different things. So this is where I have to come up with my 4 cast of characters. Okay, so my first, let me do it in different colors. So my first is x cubed. The derivative of x cubed is 3x squared. And remember, what we're doing is we're finding the derivative in terms of x cubed y to the 4th, and the derivative in terms of x of 20. So I'm doing the exact same thing. I'm giving myself some instructions, but this part right here is my product rule. So I have the first here and the second here. So my second is y to the 4th. So remember what we're doing. We are finding the derivative of y to the 4th in terms of x. This is our x prime, or our derivative of the second. Okay, so we have to be aware of this because this is where our dy dx is going to come in. So I find the derivative of y to the 4th is 4y cubed. So I've peeled off this 4, and what's left is dy dx. Okay, so anytime my variables are different, you're going to end up with a dy dx. Okay, so the minute I see product rule, I go ahead and write my forecast of characters. That way I can just plug them right in. I don't have to stop and start again. I see the product rule, I write my forecast of characters, and then I come back and I plug it into the product rule formula. So here we go. Derivative of the first times the second plus the first times the derivative of the second. Actually, I'm going to do this dy dx in a different color so it stands out. And then equals derivative of 20 in terms of x is just 0. Okay, so take a look at that. I see a product rule. I come to the side, I write my forecast of characters. I see that my y is different than my x, so I know that's where I'm going to have my dy dx. And then I plug it into the product rule formula, and now I can solve. So remember, this is what I'm solving for. I'm trying to isolate that. So I'm going to bring this part over first. Okay, so that goes away. And then I'm going to divide this off. And I'm just going to rewrite it. Usually you see these with the number in front. And because it's showing all multiplication, I can do that. Okay, so my dy dx is negative 3x squared y to the 4th over 4x cubed y cubed. And now I can simplify. So anytime you have the same variables top and bottom, you need to reduce that, just like a fraction, you need to reduce it. So -3 over 4. I have x squared on top, x cubed on the bottom. So I'm going to have an x on the bottom. I have y to the 4th on top, y cubed on the bottom. So I have 1y on the top. So that is my derivative. Okay. Yeah, go ahead, Javier.
Miss, I get lost on the -3x squared, y to the 4th, and then all of that.
Okay, so when I'm let's see, you mean like why did I subtract it?
Yeah, where the fraction comes from.
Because when I bring my 3x squared over, so remember when you are doing, let's say, when you're solving, let's say we're going to solve for x. Oops, that's a y. Okay, so we're going back to just our basic algebra, right? We're going to solve for x. This is what I want to isolate. I subtract off the 3, right? Which is exactly what I did here. I subtracted off the term that does not have my variable. And then
Okay.
I divide right here. So it's the exact same thing as just solving for one variable. Does that make sense?
Yeah.
Okay. Yeah. So that's all we're doing. That's why once you get your product rule set up and you know where your variable is, the dy dx, now I'm just going to move everything over that doesn't have the dy dx, and then I'm going to divide. And trust me, you're probably not the only one that had that same question. So thank you for asking it. All right, any other questions on that particular one? Go ahead, George.
Yeah, I guess it was kind of related to his got to the 4x cubed and y cubed.
So is it because I rearranged it from here to here? Is that what's throwing you guys off?
Yeah, I guess so, a little bit.
Okay, so because this is x cubed times 4 times y cubed, usually we see the number in front, right? The 4 usually goes in front. So I haven't changed anything. I've just changed the order of it. I just brought the 4 in the front.
Okay.
Yeah, that makes sense. Okay, I got it.
Yeah.
Okay. Yeah, so don't let that throw you. That is just, it's just normally you see the number in front. And because we have a -3 up here, I wanted you to make sure that you saw that, oh, it's a fraction, -3 over 4. Okay.
So basically, it doesn't matter where the numbers are, right?
Correct. Yeah. Yeah. We're just, our minds kind of like this x cubed 4y cubed just doesn't look right. It's not that it's wrong, it just doesn't look right. So all I did is I just rearranged it. Right? It's kind of like saying 2 times 3 is the same as 3 times 2. It means the same thing. It's just in a different order is all.
Okay, okay.
Okay? Okay, so let's jump to the next one so that we can get to the one-word problem. So on number, I'm going to do, let's see, let's do number 5. We'll skip number 4 just because I don't want to run out of time. Okay, so number 5, and it gives me more room. So when I look at this, I have a y by itself. I have an x times y squared. That's my second term. I have an x squared and a 1. So the minute I see this, I go, oh, product rule. So then I'm going to come over here and I'm going to go ahead and write that out. I want to make sure that I have all the information I need for my product rule. So the first is negative x. The derivative of the first is negative 1. The second is y squared. So the derivative of the second, so again, remember what we're doing is we're finding the derivative of y squared in terms of x. So my second one as the derivative is 2y and then dy dx. Okay, different variables. Now, the other thing that I want you to notice is you have one term with a y and a second term with the y. That means we're going to have 2 dy dx's. And it's going to be easy to solve for it, but I just want you to be aware, if I have 2 different terms with y's in them, I'm going to have 2 dy dx. So here we go. I'm going to find the derivative, the derivative, the derivative, the derivative equals the derivative. See, there's 1, 2, 3, 4, 5. So I have 5 sets of instructions. So I'm going to have, in terms of, let me get the right color here, derivative of y in terms of x, the derivative of xy squared in terms of x, the derivative of x squared in terms of x, the derivative of 1 in terms of x, and the derivative of 0 in terms of x. I'm going to put this negative on the x itself since we wrote it over here as a negative x. So this can be a plus. Okay. All right. So now you see all the information. Okay. Now we can go through and write it out the way we need to write it out. So the derivative of y in terms of x. So the derivative of y is 1. And then we have a dy dx. Now I'm going to do my product rule. So the derivative, I'm going to put it in brackets so that we can keep it separate. The derivative of the first times the second plus the first times the derivative of the second dx. Okay, so all of this is all of this. You see it? So don't get lost as to what part you've already found. Okay. And then plus. So the derivative of x squared in terms of x is just 2x. The derivative of 1 in terms of x is just 0. And the derivative of 0 in terms of x is just 0. Okay, so take a look at that and ask questions now if you have to or if you need to. So all of a sudden now we have 2 dy dx's. Okay, now that's a problem because we want to solve for one of them. So what I'm going to do is I'm going to kind of clean this up a little bit so that it looks a little cleaner. So we have dy dx. 1 times dy dx is just dy dx minus y squared. Oops, I didn't want that color. Minus y squared minus 2xy dy dx plus 2x equals 0. Okay, so I just kind of cleaned it up a little bit. And again, all I did is I just rearranged that where the 2 is in front. And I'm going to move over here so I have more room. Okay, so if you notice, this term right here and this term right here does not have a dy dx connected to it. So I'm going to move it over. Okay, thank you, Matthew. So I'm going to move these over because what I want to do is I want to isolate this dy dx. I want to get those all by itself on one side of the equal sign. So I have dy dx minus, changing colors drives me crazy. So minus 2xy dy dx equals, and then all I'm doing is I'm moving each of these over. So this negative x squared becomes a positive, I'm sorry, negative y squared becomes a positive y squared. And this positive 2x becomes a negative 2x. You see how I just moved them over to the other side? Okay. Now, if you notice on this side, I have dy dx in common. So I'm going to factor out a dy dx. So this is where your factoring skills come in, right? I'm just factoring the greatest common factor. What's left, when I divide this by this, I get a 1. When I take the dy dx off, I end up with 2xy. And then I just rewrite it. And so now I can solve for this just by dividing. So my dy dx equals y squared minus 2x over 1 minus 2xy. One minus 2xy. And that is my derivative. So I'll give you a second just to look at it. There's a lot going on. But if you look at it in terms of algebra, you have found the derivative using implicit differentiation. And then the rest of it from this point on, from right here on, it's just algebra. It's just manipulating, moving things around so that you can get your dy dx all by itself. And that's why from day one, I've said your algebra has to be on point. You have to know how to manipulate, move back and forth, how to solve for a certain variable. So that's what it all comes back down to, is being able to solve for a certain variable. Now, this is all very abstract because you have no idea what the x's and y's are. So it literally is just being able to do the algebra part. Okay. All right, so let's try a word problem. So this is our last one. Let's try a word problem. So next week we're going to get into the last section is called related rates. And so it will make much more sense because it won't be so abstract. We're going to actually find how things are changing. So how is revenue changing? How is profit changing? How is time changing? How is speed changing? All of these things that we're going to find is called related rates. And so we're going to be doing implicit differentiation, but in a very real setting. Okay, so here's an example. So you have a management consultant estimates that the number of hours per day that employees will work, right? So that's our H. So H is the number of hours, and their daily pay, which is P, are related by this equation. Okay, here's our equation. We want to find DHDP when P is 200, and then we're going to interpret our answer. So here's what this means, okay? Basically, what they're saying is the number of hours that an employee is willing to work is based on their pay. So for instance, if I'm only paying someone $7 an hour, their willingness to work is not going to be very high, right? They're going to put in their 8 hours and they're done because they're not getting paid very much. But if someone is being paid, say, $500 a day, they're going to be more willing to work and put in a little bit more time based on their pay. Okay, so let's take a look at this and see if we're finding DH, we're finding DHDP. So what this means is you're finding how many hours. So how is the hour? Let's see, how do I put this? Type it in, it will look better. So the number of hours will change based on their pay. So that's what DHDP means. We're finding how are the hours changing based on the pay. How are the hours changing based on the pay? So did you notice that the bottom variable is now DP? So what you're going to do is you're going to find the derivative in terms of P. So do you see how now being able to go through and do DDP for every term is now going to help us be able to find the derivatives much easier. Okay, so I have derivative of 60h to the 5th based on pay, plus the derivative of 2 million based on pay or P, and the derivative of P cubed based on P. So now our variables are very clear as to what is the same and what is different. Okay, so here we go. We have based on P and we have an H. So we have to do implicit differentiation. So we're going to do 300, 5 times 60 is 300, H to the 4th, DH, DP. Well, that's what we're looking for. Plus, I know I'm running out of time, plus derivative of 2 million is just 0. And now I see my P's are the same. So I'm just finding the derivative of P cubed is 3P squared. Okay, now I can isolate my DHDP by dividing both sides by 300h to the 4th. So my derivative, so how my time is, or how my hours are changing based on pay is 3P squared over 300h to the 4th. And I can reduce this to P squared over 100h to the 4th, right? The 3 goes into itself once and 3 goes into 300 100 times. Okay, so you just did implicit differentiation, finding how is the hours changing based on pay. So now we can plug some values in, right? We know P is 200. So I can plug in 200 here. But the problem is I don't know what H is. Okay, I have to find out what H is. So in order to find what H is, I'm going to go back to my original function and plug in P. So to find H, I'm going to go back to the original. So I have 60h to the 5th plus 2 million equals 200 cubed And then 60H. This works out very nicely, so hang in there. So 200 cubed is 8 million. 1, 2, 3, 4, 5, 6, 8 million. So now you're going to use algebra to find my H. I'm going to drive enough zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm going to subtract off 2 million. I get 60H to the 5th equals 6 million. Again, all I'm doing is I'm just using algebra. I get H to the 5th equals 100,000. 6 divided by 6 is 1, and then I take off one of my zeros. All right, so how do I get H by itself? Well, in order to get rid of the inverse of H to the 5th is the 5th root, right? The 5th root of H to the 5th is just H. So if I'm looking for the 5th root of 100,000, well, here's how I do it. See how there's 5 zeros? That means H is 10. Because 10 times 10 times 10 times 10 times 10 is 100,000. And I just looked at the number of zeros. Okay, so now I know what H is. So now I can take my H out and plug in my 10. So how my hours are changing based on pay is 200 squared is 4 with 4 zeros. 100 times 100 to the 4th power is 100 with 4 more zeros. So it becomes 0.04 hours. Okay, here's what that means. When you do that, and I go, this is per hour, right? So 0.04 hours. If I multiply this by 60 minutes, I get 2.4 minutes. So here's what this means. My employee, type it so that it looks better. So my employee will increase his hours by 2.4 minutes per day when paid $200 daily. Right now, that doesn't seem like a whole lot, but if you do that over a month, then it's going to be quite a bit, right? Now, what if pay was $500 per day? What would my employee be willing to do? So now what I can do is come up here and go, okay, what if my pay was $500? So 500 squared over 100 times 10 to the 4th. So I get 25 with 4 zeros divided by, what was that, 1 million? Well, this ends up being 15 minutes. So that makes sense, right? The more I'm willing to pay my employees, the longer they're willing to work. Right? But as an employer, we have to find a sweet spot, because if I'm the business owner, I want to make money, right? I want to have a profit, but I want to keep my employees happy. I want them to want to work. So you have to give some incentive without giving so much that you don't make any money as a business owner. Okay, and so you can find how much each employee is willing to work based on their pay. Okay, so that's one example of what we're going to be doing next week. We're going to do a lot of related rates, and we're only focusing next week on related rates so that you guys can have time to get ready for your next test. Okay, all right, any questions? All right, don't wait till Monday to do this assignment. It takes time. It just takes time to really get the process down. But once you get the process, it'll go smoothly. Okay? All right, guys. I will see you on Tuesday. Have a great weekend.
Bye, ma'am. Thank you so much.
All right, bye-bye.
Bye, miss. Have a
Nice
good one.
one.